All right, so this is going to be a video involving advanced quadratic relationships. The concepts that we're going to be focusing on in this video is going to be quadratic equations with complex solutions, quadratic expressions with complex factors, and quadratic structure equations. If you have not already covered quadratic equations in a basic algebra class, this video might not make a lot of sense to you. So if you haven't covered that stuff, or you covered it a long time ago and you need to kind of review it, I would review it first and then watch this video. Before we talk about advanced quadratic relationships, it's important to get an understanding of the ideas behind all of these relationships. So the first thing I'm going to talk about is the fundamental theorem of algebra. So it says right here, the fundamental theorem of algebra states that every non-zero single variable degree n polynomial with complex coefficients has, counted with multiplicity, exactly n complex roots. So that is a very mathematical definition of fundamental theorem of algebra. I'm going to try to break this down a little bit so it kind of makes sense with just normal language here. So another way of saying this is any polynomial with degree n has n number of solutions. So any polynomial with degree n has n number of solutions. And if you remember with polynomials, n has to be a positive number, okay, or zero. So what this basically means is, say I had some linear polynomial. Let's just make one up here. I'm going to go with a very easy one. So what if I just did 2 times the quantity x minus 1? Okay, and we're going to set this equal to 0 because we're looking for the number of solutions for this. Well, this function right here, this expression right here, so this expression right here is linear. So it's a linear polynomial, and the degree for it is n equals 1. Now what this basically means, based on this fundamental theorem of algebra, it means there's going to be one solution to this equation. Okay, so there's a lot of words for a very simple concept. Whatever the power is, whatever the power is for the polynomial, in this case it's x to the first, so n is equal to 1, that's how many solutions there are for that equation. So if you look at this, the answer for this equation right here is x equals 1. If you notice, x equals 1 is the only possible solution for this polynomial. There is only one. There are no other values that we can use that would actually make this equation correct. And the reason for that is the fundamental theorem of algebra. The power, the degree of this polynomial, it's x to the first, so that means there is only one answer. Now, let's do another one where instead of it being linear, let's do quadratic. And in this case, n is equal to 2. So I'm going to use the same kind of equation we already did. So 2 times x minus 1. Then I'm just going to add another one. Let's just say x plus 1. Okay, is equal to 0. Now, if you notice, this is quadratic. If you expanded this out, so what I'm highlighting right here, if you expanded this whole thing out, you would have a quadratic equation. Okay, if you don't believe me, you can kind of work that out. But again, this was covered in a previous math class. If you expand this out, it is quadratic. And since it's quadratic, it's x squared. In fact, if you looked for the expansion of this right here, what I highlighted, it would just be x squared minus 1 times the quantity 2. So it would just be 2x squared minus 2. And as you can see, this right here is quadratic. So the two things that are highlighted in green are actually equal. You can see that it's quadratic. Quadratic equations have a power of 2. And that power of 2 means there's two possible answers. In this case, the possible answers would be x equals 1 and x equals negative 1. If you plug 1 or negative 1 into this equation, this green equation, you will get 0, so it does work out. You can also plug it into this quadratic equation over here. You'll still get this being equal to 0 as well. Okay, let's keep going with this concept. Let's expand it to cubic equations. So cubic is when the n is equal to 3. So remember, n is the degree value. So this right here, degree n of the polynomial. So you can imagine some cubic function being something like this. So here's my quadratic. I'm just going to multiply by another linear factor. If you notice, that's kind of the pattern I'm doing here. Let's just say minus 2 is equal to 0. If you expanded this out, this would be cubic. Okay, you can kind of imagine, just look at the leading terms, x times x times x. It's going to be x to the third. That will be the highest possible power for that one. The solutions for this, it just so happens that there are 3 solutions. And again, it matches whatever the polynomial degree is. So whatever the polynomial degree is, that's how many solutions there are. That's basically what the fundamental theorem of algebra states. Okay, you're going to need this kind of as a fundamental understanding for the rest of this section. So that's kind of why I'm going over this first. It is also important to note that I could keep going with this instead of just doing 1, 2, and 3. I can do 4, 5, 6 to infinity and so on, and it's still going to work. It's still going to yield the exact same results. And you can kind of imagine I just keep adding another linear factor to each one of these. All right, so using our understanding of the fundamental theorem of algebra, I'm going to try to solve this problem. And if you notice, the degree for it is 2 because it's quadratic. This means that there should be 2 solutions to this. 2 solutions. And if you notice, this graph actually shows the 2 solutions. There's one right here, and there's one right here, and then they have decimal approximations for each of these. This is going to be a quick review of quadratic formula, but to actually find the exact values for these, since it rounds this off to 3 decimal places, you could use, and you should use, quadratic formula. So it's going to be x equals negative b, which is negative 3, plus or minus the square root of b squared, which is 9, minus 4ac, which is 4 times 1 times 1, which is 4. And then we're going to divide this all by 2a, which is 2 times 1. So you end up with something like this. Okay, now if we simplified it, you would end up with negative 3 plus or minus the square root of 5, all divided by 2. Okay, now if you remember before, it said that we were supposed to find 2 solutions. Okay, well, believe it or not, this right here, when I'm highlighting in orange, actually is 2 solutions because it's negative 3 plus the square root of 5 over 2 and negative 3 minus the square root of 5 over 2. Okay, so this is 2 answers because of this plus or minus thing right here. Okay, that's technically going to be 2 solutions because of that. All right, and these 2 solutions are actually right here. If you plug this into your calculator with a plus and with a minus, you would actually get those 2 answers, that negative 2.618, there'd be a bunch more decimals afterwards, and then the negative 0.382 with another bunch of decimal places afterwards. And the reason why the decimal places keep going is because this is technically irrational because we have the square root of 5. Now, another way of writing this, since we just found the roots, is to write it as in factored form. Okay, now since we have those solutions, what's highlighted in orange here, I can actually rewrite that original equation to also be equal to x minus negative 3 plus the square root of 5 over 2 times x minus negative 3 minus the square root of 5 over 2. Okay, so what I'm highlighting in yellow right here is actually equal to what I have highlighted in gray up here. Okay, those 2 values are actually equal because I wrote that in factored form. If I wanted to, I could also rewrite what I highlighted in yellow here. I could also write it based on the approximations if I wanted. So I can do plus 2.618, since it's a minus a negative, it becomes a plus. And then the other one is also minus a negative, so it's plus 0.382 like that. This would be approximate. And then this yellow down here would be the exact. Okay, so I just kind of want you to see that you can actually figure out the factored form of writing these, like what I have in the orange right here, once you actually figure out the solutions, which is what I have highlighted in orange over here. Okay. Let's go to the next one to kind of cement our understanding a little bit more. So the one we just did was x squared plus 3x plus 1. This one's going to be x squared plus 2x plus 1. So instead of 3x, it becomes 2x. First thing I'm going to do here is use the quadratic formula to solve this. So it's going to be negative b plus or minus the square root of b squared minus 4ac. So it's 4 times 1 times 1. That's just 4. And then we're dividing it by 2a, which is 2. If you notice, this right here becomes 0. So this plus or minus is kind of, it's basically pointless because negative 2 plus 0 is the same thing as negative 2 minus 0. So essentially we have negative 2 plus or minus 0 over 2, which is just equal to negative 1. And if you notice right here, that is the only solution that we have based on the graph. Okay, but if you remember, based on the fundamental theorem of algebra, we're supposed to have 2 solutions. Okay, we're supposed to have 2 solutions because right here it says the degree is 2, so that means there should be 2 solutions. This is where we go into the idea of multiplicity. And if you remember the original definition that we have here, the overly worded one, it says right here, counted with multiplicity. Okay. Now I kind of ignored that the first time because there were so many words in there. I kind of just gave you that the definition in that I'm highlighting right here. This any polynomial with degree n has n number of solutions. I didn't actually write anything about multiplicity in there because it's a brand new term. But this is a great way of explaining what multiplicity is all about using an example. Multiplicity basically states that what I have right here, it's plus or minus 0. So technically, this is -1 plus or minus 0. Now, technically, -1 plus 0 is the same as -1 minus 0. But either way, because it's plus or minus 0 with that, we call it, we say the solution for this is -1, and then we say that it has a multiplicity of 2. So it does still have two solutions. It's just that both solutions are -1. An easy way of seeing this, or an easier way of seeing this, is since we have -1 as the solution, if you just wrote x minus -1, which is x plus 1, like we did with the factored form, what we did above here, you'll notice this isn't quadratic. So the only way to actually make it quadratic is if you square it. Okay. So now what I just wrote in green here is equivalent to what I wrote in gray up here. Okay. These two things are equivalent statements. But if you'll notice, you can actually see a little bit easier where that multiplicity comes from, because that -1 is right in here because it's technically x plus 1. X plus 1 quantity squared is equal to 0, and the multiplicity comes into the fact that both of the linear factors are twins. They're basically the same thing. It's x plus 1 and x plus 1. So that's why it has a multiplicity of 2. It still does follow the fundamental theorem of algebra. It just has to introduce that idea of multiplicity to so it actually still works and makes sense with what the theorem states. So even though there's only one solution, that one solution has a multiplicity of 2, so it still does match the degree of the equation. All right, the last one is a little bit different because now it's going to involve quadratic equations with complex solutions and quadratic expressions with complex factors. So we already went over other solutions, okay? We have a irrational solution here. We did the approximate factored form for it. We did the exact factored form. We showed the multiplicity. We showed the factored form of this using the roots that you get, the solutions that you get. This one is going to be a little bit different though because it involves complex solutions. So first thing before starting this is I do want to write down that this should have technically two solutions. Okay, because the degree is 2. But if you notice, where this is equal to 0, the graph doesn't actually intersect anywhere on the x-axis. So it's never actually equal to 0 on the real number line. If we go over here, if you notice it intersects at -1, x equals -1. Here it intersects at that x equals -2.618 and -0.382. Again, those are approximate. But something's going on in this one where it's not intersecting at all. But according to the fundamental theorem of algebra, you should have two solutions. Yet we don't see any graphically. So what we're going to need to do for this is actually solve this out using quadratic formula, and hopefully we'll be able to see those two solutions. So here we go. So x is equal to -b, so it's going to be -1 plus or minus the square root of b squared, which is 1, because it's just 1 squared, minus 4ac, which is going to be -4. Okay, 4 times 1 times 1 is 4. And we're dividing this by 2a, which is 2 here. And if you notice, this part right here ends up having a negative number in the square root. And a light bulb should be going off in your head when you see a negative number in a square root, that you're going to involve complex numbers. So we're going to rewrite this to be -1 plus or minus the square root of -3 all over 2. Okay, I'm going to simplify this by pulling out that I. So it's just going to be the square root of 3 times I. And you notice it's positive 3 now because I took that the square root of a -1 out. And you end up with something like this. Now, if you notice, this does actually follow what the fundamental theorem of algebra states, because this is technically two solutions because of the plus or minus. We have -1 plus the square root of 3i over 2 and a -1 minus the square root of 3i over 2. Okay, so if you go back to the definition of fundamental theorem of algebra, it says right here, for every non-zero single variable degree n polynomial with complex coefficients has counted with multiplicity exactly n complex roots. Okay, I didn't actually say it right here. I said n number of solutions, but it could be a complex solution. So that's kind of why I wrote that there. But if you notice, this is an example where it has two complex solutions. One thing that's super important to understand with complex solutions, they always, always, always come in pairs. Okay, there's going to be one where it's a plus within the complex number, and there's one that's going to be a minus within the complex number. In this case, it's that plus or minus. So it is really important to understand that. I should probably write it down. So I'm going to write that down really quick. Complex solutions come in pairs. Okay, make sure you know that. Okay, now what you could do also with this equation right here, if you wanted to make this in factored form, you can use complex factors to do this. And that's essentially what this concept says right here, quadratic expressions with complex factors. Well, what we can do is we can actually use our solution to rewrite the original equation in factored form. So you can say x minus -1 plus the square root of 3i over 2. And then we're going to take this whole thing, and then we're going to multiply it by x minus -1 minus the square root of 3 times I all over 2, like so. Okay, what I'm highlighting in purple right here is equal to what I highlighted in gray. Okay, that is it's just written with complex factors this time. So that's essentially hitting both of these concepts right here, the quadratic equations with complex solutions and the quadratic expressions with complex factors. What I do want you to see is that once you find those solutions, you can write it in factored form quite easily. Okay, so here's the solutions here. Here is the factored form. You can kind of see how the two are related. So the last advanced quadratic relationship that we're going to cover is quadratic structure. Now, what I mean by quadratic structure, it's any equation or expression that can look like this. If it was something like ax to the 2n plus bx to the n plus c is equal to 0. So if there is an equation that you can rewrite to look like this, then it automatically has quadratic structure. And the main thing that I want you to see on this is this term right here has an exponent of n, and then this one has whatever that n is times 2. So that middle term, if you were writing it in standard form, that middle term, if you multiply its power by 2, and that's what the term is over here with the ax to the 2n, then it's got quadratic structure, okay? So you're just looking for where this doubles, essentially, from here to here. So when you see that, I do want a light bulb to be going off in your head, thinking, okay, we got to do something with quadratic structure on this. All right, the reason why it's called quadratic structure is as follows. If I were to take, let's just say u, and I was going to set it equal to x to the n, okay, I'm going to try to color code this too to make this easy to follow. So if you see right here, this x to the n, I'm highlighting that in like this pink color, is equal to this part right here. Okay, so u is equal to x to the n, okay? Well, in that case, if that's true, then what we can also do is if I wrote x to the 2n, this is technically equal to x to the n quantity squared. Okay, if you remember your exponent properties, if you have a power like this, you can just multiply those two out and you get 2n. Okay, well, what's kind of cool about this, and I'm going to go back to my highlighting here, is this x to the n right here is equal to the u. So if you notice that I try to color code everything here. Okay, well, this x to the 2n, I'm going to highlight this in orange, is equal to this part right here. Okay, so try to follow along with that x to the 2n here. So x to the 2n is going to actually be equal to, so it's this red right here, the red is equal to the u. So I'm just going to write u squared. So again, to try to color code this a little bit better, everything that's orange is technically equal to the u squared. So now what I'm going to do here is I'm going to rewrite that original equation, only this time I'm going to substitute it in with u's. So this x to the 2n, if you look right here, it's equal to u squared. So I'm just going to write au squared plus b, now x to the n is equal to u. It says it right here. Again, I color-coded everything. So this is going to be equal to u, and then we're going to add c to it, and then this is equal to 0. Now, if you notice, this is huge. You cannot use quadratic formula here, okay? Not explicitly anyway. So I'm going to write quadratic formula won't work. Okay, but since it has quadratic structure, you can substitute everything in here and make an equation here where now quadratic formula does in fact work. Okay, all right, now to try to cement this understanding a little bit more, I'm going to do a quick example for this. So let's imagine we had an equation where it was x to the fourth plus x squared plus 1 is equal to 0. Okay, what I'm going to do here is, first thing is you need to notice that it is quadratic in structure because this middle term right here has a power of 2 and then it doubles right here for 4. So that's a light bulb should be going off in your head that that middle part right here, this x squared, is what you want your u to be. Okay. So that's my u. So now I can rewrite the entire thing where it says u squared, because that's x to the fourth, plus u plus 1 is equal to 0. Okay, and the reason for this is because u squared is technically equal to x squared quantity squared, which is equal to x to the fourth, because again, you multiply exponents, if you remember the exponent properties. So all I did was substitute for x to the fourth and x squared here. So this orange highlighted equation, it should actually look familiar to you because we actually solved a similar problem, only the u's were x's. If you remember the last problem we did in that middle section, it was y equals x squared plus x plus 1 equals 0. This is just the same exact equation, only with u's instead of x's. So what I'm going to do is use quadratic formula really quick just to try to solve for, just to solve for u really quick. So we have negative 1 plus or minus the square root of b squared, which is 1, minus 4ac, which is 4 times 1 times 1, and then we're dividing all of this by 2. And then you end up with negative 1 plus or minus the square root of 3 times I all over 2. Well, that's what our u is equal to, but the problem is when the problem starts with x's, you have to solve for x. We solve for u here, but we still do need to solve for x. So what we're going to do is this u right here, what I just highlighted, is actually equal to x squared. Okay, and it says it right here. So what I'm going to do is substitute this u right here with an x squared. So x squared is equal to negative 1 plus or minus the square root of 3 times I all over 2. And then again, we have to solve for x because the problem started in terms of x, so it means we have to end it with terms of x. So that means x is going to be equal to this entire thing right here, only you have to do this plus or minus with it, but it's the entire thing with the square root. So we're going to square root both sides to get rid of that squared with the x squared, and you end up with plus or minus the square root of this whole thing right here. You might be thinking, hold on one second. The fundamental theorem of algebra states that we should have 4 solutions, okay? This one looks like we have 2 because it's the plus or minus, but actually this is technically 4 solutions. It just doesn't look like it right away. And the reason for that is because of those plus or minuses. Okay, there's 2 sets of plus or minus, so you technically have a plus plus, a minus minus, a plus minus, and a minus plus. Now that's kind of confusing, so I'm actually just going to write it down really quick so you can actually see all of the solutions. So it says plus or minus, so that means you will have the entire thing with a plus and with a positive on the outside here. You'll have one where it's the exact same thing, only with a negative on the outside there. Okay, and then you're going to have the exact same thing that we have right here. So instead of having those addition signs right here, you basically have to get rid of those and put in minuses. And now you have all 4 of those solutions, which actually is just all encapsulated in that purple. If you didn't want to rewrite the whole thing like I did in the pink here, you can do that. But if you notice, the fundamental theorem of algebra still does hold because the degree is 4 and we do have 4 solutions. Okay. It is important to understand with quadratic structure that n could be any number. Okay, n will be a real number, but it can technically be any number. It can be a fraction as long as the that middle term doubles once it gets to the squared part of it. So if it doubles going this way, you notice I multiplied it by 2, then you have quadratic structure and you can use that U substitution technique to solve for it. And again, the main idea behind this is quadratic formula won't work the way it's written, but if you rewrite it, then quadratic formula does work. You can use the quadratic formula like I did down here and solve, and you still find all of the solutions. So, all right, so that's basically a snapshot of this entire section of advanced quadratic relationships. If you have any questions about anything in this video, let me know.